Yeah.
Okay, good. So can you still see the screen?
Yes.
Good. Okay, so then let's continue with the first lecture, which was a quick tour of polylogarithms and correction. So Ruth in her lecture, as I said, will cover polylogarithms much more in detail and also correction. But I want to give you a brief glimpse, and also as a starting point for generalizations, and I urge you to look at the other lectures. So in order to get started, and to see what these generalizations are, let's start from the following exercise. Imagine I give you a rational function, and I tell you that this function has at most poles at certain places. The complex plane. Call these places A1 to AN. Well, clearly such a rational function must have this shape, right? There's no other choice. Must be some polynomial divided by some powers of x minus AR. How can you compute the integral of this rational function? Well, I guess you all know how to do that. The first step is the partial fraction. If you partial fraction, then you quickly realize that the only things that you need to understand is how to compute integrals of powers of x or of powers of inverses of x minus AR. Those are the only things you need to understand. And those are easy. And so the primitive of x to the k is just proportional to x to the k plus 1. And the same for the other one, where you get 1 of x minus a to the power k minus 1. But the important thing is that you have this prefactor. You see that this prefactor is singular when k is equal to 1. And we all know why. That is because this formula is only valid when k is not 1. When k is equal to 1, you don't get another rational function, you get a log. So the conclusion is that if you start from a rational function and you compute its primitive, the integral over it, the result will only involve rational functions and logarithms. Right? Proof its justice, the exercise we made, the partial fraction and the integral. If you iterate this argument, you conclude that if you compute, say, an iterated integral of a rational function, and here I'm a bit vague, but I think it's you get what I mean. If you iterate it, then look at rational functions, logarithms, and say if you do it twice, you could also get dilogarithms, because now you would have integrals that involve logarithms and things like log divided by t, and then integrate gives you dilogarithm, and so on. So in general, you can think of it as the polylogarithms arise from a geometric situation where you have a Riemann sphere, that's complex plane, and you mark some points, or you can also say you remove them. And you ask yourself, okay, what are the meromorphic functions on this sphere where you remove some points? Well, those are the rational functions with poles at most of these places. And now you go and you take a path and you integrate some rational function on this space along this path. And by the argument that I just gave, you can easily see that such an integral where you well, an iterated integral along this path would be expressible always in terms of rational functions and multiple polylogarithms. So multiple polylogarithms, you can think of them as coming from geometry. They're the result of computing iterated integrals on the Riemann sphere, where you have marked some points, because that's where you allow the functions to have poles. And in that sense, I guess you can also see why polylogarithms, well, we started from them. Those are the simplest objects you can get in this framework, because there's essentially no simpler geometry than a sphere, and the points are just the locations for the poles. But once you accept that, you can also, well, you conclude that it must also be possible to generalize this construction to consider more general iterated integrals, where this underlying geometric space is different. For example, instead of starting from a Riemann sphere where you mark some points, you start on the torus where you mark some points, or even other geometric objects. Okay. And well, we said the sphere is the simplest geometry. What is the next simplest geometry? Well, that would indeed be the torus. And you see that is, well, if you know what Riemann surfaces are, right? The Riemann sphere is the Riemann surface of genus 0, the only one. And if you go to genus 1, you get a torus. Now you could even imagine going to geometric objects that are more complicated in Riemann surfaces, so higher dimensional objects. But for now, let's look at the next complicated example, which is what do you get if you look at iterated integrals on the torus of marked points. And that brings us to the topic of elliptic curves, elliptic polynomials. So we'll start with studying elliptic curves. And once you understand that, then the definition of elliptic polylogarithms comes out much more. So what is an elliptic curve? An elliptic curve, you can think of, well, the naive way to think about it is as follows. Imagine you consider the set of points, x, y, that are solutions to a polynomial equation of this type. So y squared equals a polynomial of degree 4. Okay, and the polynomial of degree 4, I can always say it's of the form x minus a1, x minus a2, x minus a3, x minus a4. Such a set of points, you can call it an elliptic curve, but that is an elliptic curve. It's an example. Note that I could always change coordinates such that one of these 4 zeros of my polynomials is an infinity type, more formal, more projective space. And then the same geometric object could arise by using a polynomial of degree 3, so cubic. So I will often switch between quartic and cubic. It is the same. The cubic polynomial would be the quartic polynomial where one of the zeros lies in infinity. Okay, so what does such a curve look like? Well, you see one here. So assume first, well, assume here that these a1, a2, a3, a4 are real. Yes, of course, if they're not real, then we cannot draw them. And of course, I can also only draw the points xy that are real. But I'm actually looking at it over the complex numbers. We will go back to complex picture in a second. But for now, let's look at the real points. So if a1, a2, a3, a4, and I order them this way, and you can easily track that the curve y squared equals p4 of x, this is that curve, what looks like this curve. Okay. particularly see it's symmetric along the x-axis. That is simply because you easily see that if y is a solution, then also minus y is a solution. And you also see easily that the only points that correspond to y equals 0 are those that correspond to x being a1, a2, a3. Okay, so the only points where your curve will intersect the x-axis are these 4 points in 1, 2, 3. Okay. So that is what this curve looks like. Okay, so we decide that for every point x I that is not sorry x that is not equal to one of the AIs, I always have 2 points, y and minus 1. And I will often use the notation here like y sub x to say that is the value of y that corresponds to the point x. And say the value of y corresponds to point x by choosing, say, the plus sign for the square root. Specific sign for the square root. So I always have, for every point x, I have 2 solutions, except for these 4 points they are. They only have 1. Now, this allows me to do the following. So imagine I want to choose a set of local coordinates. So imagine I pick here a point x, y on my curve, and I look at a little neighborhood on that curve. And I ask myself, how can I choose a local set of coordinates in this green neighborhood? Well, I guess you can easily see that just specifying the x coordinate will be enough. Okay, in this neighborhood of this point x, y sub x, specifying this x coordinate is enough. So whenever x is not one of the AIs, I can use x as a local coordinate on my curve. However, you can also easily check that in the neighborhood of one of the AIs, that will never work, because in the neighborhood of AI, I always have in this neighborhood at least 2 different points that have the same x, right? Like these 2 which have the same x, for example. So x alone is not good specify a point in the blue. So x, I can use it as a coordinate, as long as I'm not in a neighborhood of what is called the branch points, which are really nice. So that's why I will often just use x, but at x I mean the choice of local coordinate. It's always a good choice of local coordinate, except in neighborhood of the branch. So that was now what this looks like if I look at the real picture. What do I get if I look at it from the complex point of view? So now A1, A2, A3, A4, while they may still be real, but they could even be complex. And well, if I imagine I pick x as my coordinate, so this coordinate pattern would look like complex x plane. And the value of y I just calculated from x for a specific choice of the root. So locally, I fix my neighborhood and I choose x as my coordinate, it looks like a complex x plane with the 4 special point A1, A2, A3, A4. And I have the square root. And because of the square root, I have put two branch cuts into my complex plane, which mean the following. So, for example, if I turn around A1, I will change the sign of the square root. Right? Because if I change, if I let x turn around A1, but not around any other of the AIs, the phase of x minus AI, A1 will change by 2 pi I. So the square root will make the phase change by I pi, so I change the sign. So that's the meaning of this branch cut. So when I cross this cut, we go around A1, but not around any of the others, I change sign. Clearly, if I go around 2 of the branch points at the same time, I don't change sign, because now both x minus, for example, here for the green curve, both the contribution from x minus a3 and x minus a4 would change sign. So if I go around the green loop, I don't change sign. So that's the meaning of my branch cut. Note that I chose them here to be between a1 and a2 and a3 and a4. That is convention. It's immaterial in the end. I could have also chosen them between a1 and a3 and a2 and a4. The picture would be the same. I just have to choose them somehow. In such a way that there's one branch cut that starts or ends on the AI. Okay. So what does that mean? Well, you should picture it as follows. So now let me draw the complex X plane again as the sphere. So this represents now the Riemann sphere that I get by compactifying my complex X plane. And I have these 4 points and these 2 branches. And so let's take this idea of, well, and actually I need 2 of these copies because I have one copy, one complex X plane for the positive square root and one for the negative square root. Because to one value of x, I can associate 2 values of y. And how are they related? They're not completely independent. Well, they are related by going in a closed loop around one of the branch points, because then y changes sign. So if I go in a loop around branch points, I must jump from one of these copies to the other. And I can do that as follows. So I cut open my 2 complex planes along the branch cuts. And I get 2 kind of tubes, or if you want to, balloons with 2 holes. And I glue them together, because now what that means is that if I go, for example, around this loop here, that corresponds now to something like this. It means going here and then ending here, which is now glued together with this point here. So it's like going like this. Like this. Okay. So indeed, now if I go in a closed loop around one of the branch points, I end up on the other Riemann sheet. So these 2 Riemann spheres that I had up here, those are nothing but the different Riemann sheets. And I glue them together to get a new geometric object, which in this case, well, you can see it has the shape of a torus. That's the topology of torus. And I got that by gluing together 2 complex planes that were cut open along 2 branches. So from that, you can see that topologically, the elliptic curve, when you look at it over the complex numbers, is topologically a torus. Okay, so elliptic curves are the things that we wanted, because we said, well, the next we had the Riemann sphere and iterated integrals on that, and now, well, we want to go to tori. We need elliptic curves. So now we also need this. What is the equivalent of a rational function, but for such a torus? Well, it's actually relatively easy. The only natural thing you can do is to say, well, now I have my points x, y. So let me write down rational functions in x and y. the only thing I have. Well, of course, x and y are not independent, but they are subject to the constraint that y squared is equal to this polynomial, because I have the polynomial constraint. That's where I started. I guess you can easily see, and if you can't see it, I leave it to you as an exercise, that every such rational function, so to say, if you take a rational function in two variables and they are subject to this constraint, then the most general thing you can write down is a function of this type, or equivalently a function of this type where R1 and R2 are just rational functions in one variable. Leave it to you as an exercise to show that that is the most general thing I can write down. So I have now the equivalent of what a rational function is, but now for my elliptic curve. And so now I can play the same game as what we did for the Riemann sphere before, where we integrated rational functions. We asked ourselves what kind of functions can come out of integrating a rational function in the Riemann sphere. And well, I guess you can easily see that this contribution from R1, well, let's just integrate a rational function. That gives me rational function in logs. That's not new. If there's something new, it will come from here. Because that's where I have this dx over y. And remember that y is actually, well, y or y sub x is actually square root. So this new piece will be an integral that involves rational functions in x, but it's also the square root of this polynomial. And again, we can proceed just like with partial functions, we can partial fraction. The y doesn't interfere with the partial fractioning. And you can see that the only things that you need to consider now, before it was powers of x and powers of inverse powers of x minus something. Now it would be powers of x divided by the square root, or these inverse powers divided by the square root. So the only integrals I need to understand are those. Now, because formulas are simpler, I will from now on look at the case of cubic polynomial. Remember that there's no substantial difference between polynomial of degree 3 or 4, because I can interpret this polynomial of degree 3, but the constraints coming from this polynomial of degree 3 as coming from polynomial of degree 4, but where 1 to 0 is like. But it's much easier to write down the formulas for the cubic case. Good. So what can I do? Well, I leave it to you as a homework to show that the following formula holds. Y, I remind you, is always to interpret it as the square root. And the following formula holds. So if you take y times power of x, you differentiate it, you get a sum of terms, sum of 4 terms to be precise. They're all of the type power of x divided by y times something, which is a complicated expression, but is essentially, it's a constant in x. Why do I care about that as well? My goal was to understand integrals. So let me now write an integral sign on each side of this equation. And then you can easily see, of course, that here you have a derivative. So you get the integral of derivative. So actually the left-hand side of this equation will be trivial. And the right-hand side will now give me a recursion. Well, I will have left-hand side will be a simple object equal the sum of these 4 integrals for different powers of the exponent of x. So in other words, I get a recursion for these integrals of the type dx over y times powers of x. Now this recursion has depth 3, by which I mean is that, well, see that every I have 4 terms in the sum. So there will always be 3 objects that I cannot fix because I need to specify 3 objects to calculate the 4th one for my recursion. So there will be 3 left. We cannot eliminate everything. There will be 3 left. I can choose them to be x to the power 0, this here, x to the power 1, and say x to the power minus 1. So the conclusion is that every integral of this type here, using these identities, will always be expressed in terms of rational functions. And then just these 3 integrals down here, the integrals of these 3 differential terms. Now you can do exactly the same, you can play exactly the same game with this guy. And the conclusion will be that every integral of this 5 dx over y times a rational function will be reducible to any of these 4 objects here. The blue one, dx over y, x dx over y, dx over y, x minus c, which comes from here. But also for c equals 0, you would have what we had in the previous slide, which was dx over y times x. C equals 0. And also, I should also include here this bit, because remember we had this piece with R1 before. Right? There was this piece here, which we said gives me logs. So logs are integrals of dx over x minus something. So when I get this, what I had already for the Riemann sphere, which was dx over x minus c, plus 3 new objects. The first one is often called in the literature the differential of the first kind, or holomorphic differential. Holomorphic. And you can actually check that there's indeed no pole. You can say, why there's 1 over y? No, if you actually carefully check it, you can see that there's no pole. In order to see that, you have to keep in, for example, keep in mind that the zeros of y are precisely these branch points. But x is not a good coordinate in the neighborhood of the branch point. So you have to change coordinates to a good set of coordinates, and then you see that there's no code. If you compute this integral, you will always be able to evaluate it in terms of what's called an elliptic integral of the first kind, whose definition is C. This k of lambda is a special function. It's called elliptic integral of the first kind. And the integral of dx over y will, but actually a bit quick here. It should be, this is one example, could be what's called incomplete elliptic integral of the first kind. I'll show here the special case of it is complete elliptic integral. Then you also get integrals of this x dx over y. This is what is called the differential of the second kind. Now you can show that this differential has a pole, in this case at infinity, but the residue of that pole is 0. In order to show it, you have to do exactly the same change of variables you would need to do for the differential of the first kind to show that there's no pole. If you do the same calculation for the differential of the second kind, you can see that it has a pole at infinity, but no residue. And the integral of the differential of the second kind, you can always evaluate it in terms of, here again, I show you it's called complete elliptic integrals and more generally incomplete elliptic integrals of second and first kind. The second kind is called E. If you evaluate it, you get E and K, you get both. Why do you get both? Well, the first kind had no pole. So if you start with something which has a pole, of course you will get the thing that has a pole, plus possibly contribution from things that have no poles. And finally, there's this last guy. That one now clearly has a pole at x equals c. And that is called the differential of the third kind. That is, it has a pole, first a simple pole, so pole with residue, but also dx over x minus c. So also this guy is the differential of the third kind. One comment here is that for this guy, C should not be equal to branch point. You can actually show, if you're careful, that whenever C is equal to one of the i's, you can write this guy as a total derivative and you get it with you. So there's an additional restriction here. So what is the upshot? The upshot is that while we said at the beginning, we started on the Riemann sphere. When you start with a rational function, you do an integral, you get a rational function, and you get lobes. And then if you iterate this, you get a rational function, you get multiple polynomials. If you play the same game now for an elliptic curve, you start from a rational function with elliptic curve, you do the integral. You get rational functions, but now rational means that it also depends on y, right? Rational means a rational function on the elliptic curve, so it has x and square root. And then you get logs, which are the result of this guy here. You get, that's what gives you this. Then you have the elliptic integrals of the first, second, and third kind. And so now, I guess it's clear what elliptic polylogs are. You can, just like with the Riemann sphere, you can iterate this construction. You end up with rational functions. You end up with polylogs, those you get from iterating the log. But now I can also iterate these elliptic integrals. Those produce new functions, which would neither be the elliptic integrals that you find in textbooks, nor will it be multiple polylogs. They will be new objects. They will be iterated integrals where your kernels, these FIs, roughly speaking, and this which I'm saying now is not quite correct, but in your mind, they should be FIs at home in this section, roughly speaking. We'll clarify this in a bit, but that is the idea. So all the things that you cannot trivially integrate, you're stuck with them. And if you build iterated integrals out of them, that's what you get. And that's what in first approximation you can call elliptic polylogs. There's a caveat which we'll address in a bit. Good. Okay. So we will now, so that is what elliptic polylogs are. For explicit definitions, we will go and have to change here and describe the elliptic curve in a slightly different way. But before we do that, let's look at the following called the two corollaries. Without even having seen explicit examples of elliptic polylogarithms, you can write down some examples of them. Because the first thing is that all normal polylogs are also elliptic polylogs. Why? Well, because if you take this naive definition that every iterated integral you can build out of these four differential forms here would be an elliptic polylog, well, in particular, these forms would give you normal polylogs. So all normal polylogs are also elliptic. The other example of elliptic polylogs that you can imagine are normal polylogs whose arguments are rational functions on the elliptic curve. So they depend on x and y. They are rational, but they depend on x and y. Well, y is constrained to be y squared equals p4x. All those functions will also be elliptic polylogs. This is slightly less obvious than before, but you can show it recursively if you differentiate it. You can actually leave it as a homework. If you differentiate this such a function with respect to x, and you use the fact that y squared is equal to polynomial of x, and then you can recursively show that all these functions are elliptic. And the other thing I think we should mention at this point is that where do these things show up? They show up, well, I guess many of you know, for the so-called two-loop sunrise experiment. And for simplicity, let me take the equinox. So look at the two-loop integral where I take three equal propagator masses, m is non-zero. And I can go to Feynman parameters. So this, you see here the loop momentum representation of the integral. You can also go to Feynman parameters. And I get a threefold integral of three propagators, the delta function. And the integrand is just 1 over f, where f is of course the second Zemanzik polynomial, and it's shown here in this one. It's a cubic polynomial. And of course, it can put x equals x3 equal to 1. You can put x3 equal to 1, and you can easily check that it can do the integral, for example, in x2. And let me also change variables from x1 to x in this way. And you can check, and then leave it to use an exercise that if you do that, then, well, you eliminate x3 from the delta function, x2, you just integrate from 0 to infinity, and it gives you a log, and it looks like this. It looks like, well, you get a log from the integral of x2. And you also get dx over y, where y is the square root of a polynomial of degree 4. And I show you the zeros of this polynomial here. This would be the 4 branch points of the picture. This guy, the O, is related directly to the ratio of the mass to momentum. And so, what about the last integral? This guy of x? Well, let's think of it. So, this is dx over y. That clearly is precise the integration measure if you want. And in there, let's take this integral and let's maybe go to another slide. So you see here that this is of the type, well, this is of the type, well, let's try to do this log of some rational function in x and y. So that, we just said, is an elliptic polylog. Okay, because remember that we had this corollary that said every multiple polylog with arguments a rational function on the curve are elliptic polylogs. So this differential the first time multiplied by an elliptic polylog. So this will be an integral precisely of the type that we discussed. That gives you an elliptic polylog. And it cannot be a normal polylog because you have the square roots y everywhere. Remember that y squared. So from that, you can see that this integral is can do it because and I need to use an example as an exercise to take this rational function here, call it f, so compute dx of f, and then write fx as an integral over whatever you found, well, and to show that f of x is indeed an integral of these four differential forms. They will look slightly different because they were quartic polynomials. So you may first want, for example, to do a transformation that sends one of the points to infinity, you get cubics, and then you would see that this function f of x here, you can indeed write it as a linear combination of these integrals and discuss the integral of these differential forms. But then you have this other integral to do, so you get the iterated integral of length 2. So in that sense, you can say that the equal mass Summer's integral is an elliptic dialog. And the last comment I want to make for today is that you see this is variable t left over. And that is actually the kinematic variable times square of p squared. This t appears here in these rows, and these rows appear in the branch points. Now, that means that if I change the kinematics, I change m or change p, I will change t, I will change o, so I will change the one. So I guess you can see that if I change the branch points, I will change the shape of the torus. Okay? So the shape of the curve. If I move the zeros of the polynomial, I get a different curve. So for example, for one choice of a's, I may get a very thick donut. For another choice, I may get a very thin donut. But those are not the same. Changing the kinematics amounts to changing the shape of the elliptic curve. We'll come back to that tomorrow. But I want you to remember that actually kinematics is encoded on the shape of the elliptic curve. It is changed the choice of the branch points and so In this case, 1.10. Okay, I guess this is then a good place to stop for today, and then we can resume tomorrow.